Okay, now we're moving into section 6 of chapter 14 in Brown and LeMay. And in this section, so we've been talking about kinetics, we've been talking about reaction rates, what activation energy, things like that. So now we want to talk about, well, what's the actual mechanism that a reaction might occur, and how might that impact the kinetics and the time that a reaction takes. So the sequence of events that describes the actual process of by which reactants become products is called the reaction mechanism. So it's kind of the steps that they take. So some reactions might occur all at once, but it's also possible that a reaction might actually go through 2 steps or 3 steps. So a multi-step process that can actually be defined or kind of predicted in the process. So each of these processes is known as an elementary reaction. So if you broke it down into multiple mechanisms, then each step, each reaction would be known as an elementary reaction or an elementary process. So a reaction that only requires one, an elementary reaction that just has one reactant in it is called a unimolecular elementary reaction. Okay, and you can see its rate law there. So rate law is equal to K times the concentration of A. So that would be a first order reaction or first order elementary reaction. And then other ones that we've looked at are bimolecular, so where you need 2 things. So those are second order reactions. And then you get to termolecular, where the reaction requires 3 reactant compounds for it to go forward, and those are very rare. Keep in mind, termolecular reactions or tertiary. So you have your first order, second order, and a third order reaction is very rare to occur, because basically what you're saying is that you're going to need 3 reactants colliding at the same moment or coming into contact at the same moment for the reaction to go forward. So that's obviously going to be a rarity in a single reaction. So we'll look at that a little bit further. But when we talk about a multi-step mechanism or a reaction where it takes several reactions to actually get the products that you want, often one of those steps is going to be slower than the other. So imagine with the diagram down below. So you've got traffic going through the city. Obviously not Blaine. So think of like a large city like Seattle, or you can even think of Bellingham. And maybe so all these cars are going down this road, and Plaza A has a lot of traffic or something that slows it more often, and then Plaza B, by the time the cars get there, nothing's really there to delay it, so everything goes through. So that would be the idea that the first reaction is the slow reaction, and the second reaction is the fast reaction. And then the second example here is that the first plaza is easy for cars to get through, but the second plaza is the slow one. And so this would be the idea that the first reaction is a fast reaction, you just crank through, but the second reaction is the slowing reaction, and that impacts the rate at which a reaction will occur. So what we would call the slow reaction, we would call it the rate determining step. It is the thing that limits how much product we can make, limits how fast we can make that product through the process. So how does this apply? How do we utilize this? Well, if the slow reaction is the initial step in the reaction mechanism, then the rate law is found experimentally through just determining the rate of the first reaction. And so here we have rate equals K, the reaction constant, times the concentration of NO2 squared. So it's a second order reaction. So CO, we know that CO is necessary because it's part of so this is the overall reaction, but the rate of the reaction seems not to depend on the CO2 that's in this reaction reaction equation. So what that tells us is that, okay, there must be a step or a mechanism that does not include CO, and that mechanism is what is actually determining the rate. So the CO must be in like the fast reaction, where the NO2s must be in the slow reaction because they're part of the rate equation. So let's think about the steps here. So if we go to this next slide, so this is one proposed mechanism for how this reaction actually occurs. So what happens to start with is you have two NO2 molecules. They come in contact. They have some type of collision, and one of the oxygens attaches to one of the NO2s, and then you have an NO. And then the CO that is present in the reaction then interacts with the NO3, and it takes one of those oxygens, and then you have an NO2 left behind. And so the slow reaction is that first reaction because that is what determined the rate equation. And this second one is so fast that once NO3 is produced, bam, it comes in collision with CO and it's gone. You have your final products. And so what determines the speed of the whole reaction is just the first reaction. The second one just kind of flows through. And that intermediate is consumed in the second step, so therefore it doesn't show up in the final equation. All right. Now, so that was when your first reaction of the mechanism is the slow reaction. But now the trickier one is when the slow reaction is the second in the order. So here we have an equation, okay, a reaction where you have 2NO plus bromine gas produces 2NOBr gas. So we have a rate law here, and if you look at the rate law, it includes 2 nitrogen monoxides, but it also includes bromine gas. Now, one thing to note is that, so this reaction makes it look, so with this rate law, makes it look like it is a termolecular process. Okay, so where like all three things have to collide at the exact same time. Now that is probably very unlikely. It's very unlikely that you're going to have a termolecular process present. So what that most likely indicates is that you have a reaction where the second step is the slow reaction, and so that changes the rate law than what you would normally expect. So here are a proposed mechanism for this reaction. So where your fast reaction is NO combining with Br2 to make NOBr2. And then you get this second step where it combines with NO again, and the Br gets broken up. Now, you notice how the first step has the arrow between the products and the reactants has a reverse and a forward. And that's because if that's the fast reaction, you're going to have NOBr2, but there's going to be an equilibrium present where it's going to go back the other way as well. And so with that, we want to put that back and forth arrow, and we'll see how that plays out a little bit further. So the rate of the overall reaction depends upon the rate of the slow step, so that second reaction that we just saw. So the rate law for that step would be, so rate is equal to K2, okay, the constant, times the two reactants there, the concentration of the NOBr2 times the concentration of NO. But we need to find the concentration of NOBr2 because we don't know that. And so what we can do is we can look at the relationship between NO and Br2 in the beginning step. Okay, so since it's at equilibrium, reactants and products of the first step are in equilibrium, then the rate final is equal to the forward rate is equal to the reverse rate. So what we can do is we can make those equal to each other. Notice how the K values, there's a positive and a negative, just so that we're kind of keeping in mind that you would have different constants for this. Okay, and we can manipulate that top equation around so that the NOBr2 is isolated. Okay, and now we have an answer for what the concentration of NOBr2 is equal to. It's equal to that all those Ks and the NO and the Br2. Now, we're not going to do much with that. We're just going to plug that information into the larger equation, okay? So that the rate is equal to all the Ks kind of lumped together times the NO, the Br2, and the NO. So we combine them all together, and we ultimately get the KNO2Br2, and we're kind of confirming that the mechanism that we suggested is supported by the experimental rate law that was determined and that we had at the beginning of this question. Now, this stuff is challenging. Like I've said, kinetics and rate law stuff is challenging. So I really need you to kind of pull up your bootstraps and work really hard at trying to grasp some of these kind of obtuse ideas, and also come in for extra help and work with me, and we can kind of work together on solving this stuff. And I love working and solving this stuff, but this stuff is even challenging for me to really kind of keep track of what's going on. So please take advantage of extra help when available. All right, that is it, and I'll pop in tomorrow, but I will see you on Tuesday.